Hello everyone, I'm Karen and I will be talking about pH buffers in this video. So for pH buffers, before we start with the equilibrium curves, let's take a look at the Henderson-Hasselbalch equation. So as we all know that the Henderson-Hasselbalch equation is pH equals pKa plus log of base, concentration of base over concentration acid. This is used for weak acid and its conjugate base, used for weak base and its conjugate acid. You should also know that if the pH is greater than pKa, then the solution is more basic, and if the pH is less than pKa, the solution is more acidic. The way you'll figure that out is that if you subtract, if you do pH minus pKa, and you get a positive number, then you have more base, because log of a positive number of a number greater than 1 will be positive. However, if it's a log of a number that's less than 1, which would give you a negative on this side, it would be more acidic. We would know that there's more acid in the solution than base. So she also talked about common ion effect. So adding a common ion suppresses a reaction that produces the ion. So let's say you have H2CO3 plus H2O and then HCO3 minus plus H3O. Right? Naturally, if we have more reactants, the reaction will move to the products to form more of the products. However, if we want to stop the reaction from moving forward to produce the product, if we add an ion that's similar to the products, it will tell the system that we've had enough of this and you shouldn't be moving forward, right? So as this said, in order to suppress this reaction, we must add a compound that includes carbonate, right? Because this is carbonate. CO3 is carbonate. So if we add NaHCO, CO3, we can shift the equilibrium to the left. This is supposed to be O3. My bad. So let's do an example of that. So let's say the question says, calculate the pH of a solution that is 0.25 molarity in methylamine and 0.75 molarity in methylamine hydrochloride. And it gives you that the pKb of this solution is 3.36. So again, note that you're given pKb, not pKa, right? So the equation that we have usually says pH equals pKa plus log base over acid, right? So here we have pKa. So we have two options. We can either use this equation, but we have to do some conversions. We also can use the other equation, this one, but we also have to do other conversions. So note here that this one is POH instead of pH. Note that this is pKb instead of pKa. And also note that it's log of acid over base rather than base over acid. So you have to remember, if you want to switch equations, be able to know that there are differences and that you should pay attention to these. So let's see. So if we use the first equation, right, we must first convert pKb, which was given to us, to pKa. And you do that by subtracting pKb from 14 to get pKa, right? So, however, if we want to determine, if we want to use this equation because we are given pKb, we can remember to convert at the end the POH to pH, because the question asks for the pH and not POH. So again, remember that pH equals the 14 minus POH. So when you do these calculations, plug in the numbers, you should get 10.16. No matter which equation you use, you just have to remember to do the right conversions. So some facts about pH buffers. So a pH buffer is a solution that resists changes in pH when acid and bases are added to it, typically a solution of weak acids and its conjugate base. It can also be weak base and its conjugate acid. Common ion effect plays a key role in controlling pH. Again, when we mentioned that at the beginning of the slides, that means you are tricking the solution by adding a compound or an ion that's similar to the one in the product in order to tell the system that we have enough and you shouldn't be working, you should be going in reverse direction. Weak acid component neutralizes the added base, and weak base component neutralizes the added acid. Makes sense because they cancel each other out. So ideally, similar concentrations of both components will give you a stable buffer. So now let's talk about titration curves. So as you see here, we have, it starts from pH of 2 and it goes all the way up. So this is the pH scale and this is the volume scale. So you should know that this is called the midpoint. So when it's almost flat and getting to equivalence point, you should know that this is called the midpoint. At the midpoint, you should know that it's halfway to equivalence point. So this volume is 10 and equivalence point is at volume of 20. So you should know that when you double the volume, you're going to get the equivalence point. You also should know that the midpoint in titration curve of a weak acid is where half of the weak acid initially is converted to its conjugate base, right? So that means that we have the concentration of the base equals the concentration of the acid because half was converted. You should also know that the pH equals the pKa. Now at equivalence point, you should know that that's where your solution is considered neutral. You should know that for a stronger acid, when you add a base, it will be around, the pH will be around 7 when it's neutral. However, for a weak acid and you add a strong base, the equivalent point or the pH will be higher than 7, which here you see is 8.73. You should also know that if the line starts from below 2, usually, that's a very strong acid, right? We can see here it's hydrochloric acid. But if you start from above 2 and it curves that way, it's usually a weaker acid. So strong acid and weak acid. So these are the general and basic rules that you should know about titration curves. If you start with a weak base or a strong base, the curve will go from here up, down, and this way instead. So let's see if I can draw it here. It would go something like this instead. And this would be considered a strong base. However, if you want a weaker base, it will be like this. They will both end the same way. So moving on. Let's see. So, I have to erase this. So now, for this last slide, we're going to apply titration to buffers, right? So if you add a strong acid to a buffer, you're going to have the strong acid plus the weak base that you already have, and that will yield a weak acid in water. So the weak base has been converted to a weak acid and then water. And here we know that the pH will be decreasing since pH is higher for a weak base and it's being an acid, so it's automatically going to go from higher than 7 to lower than 7. Let's see for here. Adding strong base to a buffer will give you a strong base plus a weak acid and a weak base plus water. And that will cause the pH to increase. So your weak acid, is converted to a weak base. And that's why your pH will be increasing. So thank you for watching, and our next video will be more in depth about the equilibrium curves and the rise tables. But yes, thank you for watching.